So we're going to proceed sort of with expanding on what you've learned about forces and how they have directions and components. We're going to continue on with that and sort of introduce real forces. The first real force, we're going to talk about two different kinds of forces today. One of them is
gravity?
Is the force of gravity. Yep, force of gravity. And as you might suspect, gravity is always pushing down. So if you're wondering which way the force of gravity, at least if you're on Earth,
it's always going down.
Yep. So if you're exactly. Yeah. And now we're going to play around a little bit with changing our coordinate system. So you think gravity will only have a negative y component, but if we rotate the coordinate axis, then it can have an x and a y component in that other axis. So we'll show you an example of that today. But first, we're just going to start out on a flat surface, and we're going to consider a block. And now, in order to compute the force of gravity, we're going to have to give our thing, we're going to have to consider what is the weight of an object.
You have to give it mass.
Yes. So the mass is always going to be measured, well, it's measured, there's all different units. There's pounds, there's grams, there's
But kilograms is more common.
Kilograms is important because our unit for force, which is the Newton, can actually be expressed in terms of other units we're more familiar of. A Newton actually is a kilogram meter per second squared.
Oh.
So a Newton isn't, I mean, you can think of a Newton as a unit of force, but a unit of force is actually a mass, and then this meter per second squared is an acceleration. And we'll talk about acceleration and velocity another day. But we're going to get into Newton's laws of motion, which in fact today though we're going to calculate the force of gravity, because gravity accelerates everything towards the center of the Earth. All right.
Because that's where.
So if I were to try to pick up this 10 kilogram mass, I want to calculate the force I would need to cancel the force of gravity so that I can move it. Right? Because if gravity has a stronger force, so here's gravity. If gravity's force is stronger than my force, so here's F me, and here's F gravity. If gravity's force is stronger than my force trying to pick up this 10 kilogram block, what do you think is going to happen?
Well, the block will stay there.
Yeah. The block won't move up. In fact, if the floor were to break, it would actually fall through the floor.
Yeah.
But if the floor is strong enough to hold to counter the force of gravity, at least the block won't fall through the floor.
But which usually is force tend to be.
I won't be able to pick it up if I can't overcome the force of gravity.
Yeah, gravity. Yeah.
So, if we can calculate the force of gravity, then we can calculate the force we need to move an object. Because once we counter the gravitational force, say we exactly counter it, what happens then? Well, the block still doesn't move. If we just even slightly exceed it by just the smallest amount, though, we'll be able to start moving.
Just slightly move it up.
And it will keep moving up as long as we apply that force. So, now, in fact, what we're going to learn later when we talk about velocity and acceleration, once we accelerate the body so it's moving, we actually only need to balance the force to keep it moving. An object that is already in motion will stay in motion unless an external force acts on it. So if we balance the force of gravity, so let's say we exactly balance the force of gravity, then we manage to overcome it just briefly to make it be stronger. So we actually get it moving. Once it's moving up, as long as we apply enough force to counter gravity, it will keep moving up.
Like, take a car in motion and
Yeah.
you're going up a hill with gravity. If you have already moved it around the parking lot before it reaches the hill, and it'll slow down, but it'll still have enough force to, like, move up.
I'm not sure what you mean by all that. I'm talking about in a world where there's no other force except gravity. When you're rolling around in a car, there's the force of
The
friction.
car has its own
And we will
force of
talk
friction.
about friction today.
That.
You're gonna get that's the second force we're gonna talk about.
Cool.
The force of gravity is easy to calculate. So it turns out F gravity
FG.
is equal to the mass of the object times what we call little g. And little g is the acceleration of gravity. Now, if it were a universal constant, I wouldn't use a little g here. Okay? I would just say, in the case on Earth, so we'll call G Earth, 9.8 meters per second squared. But this G Earth is dependent on being on Earth.
Mhm.
Yep.
If you were on the moon, this little g would be different.
No.
And if you were on Mars, it would be different. If you were on the moon, it would be like 1/6
Mhm.
of this. It'd be like around
The little
1.5
G.
or 6.
It would be much smaller.
It'd be like 1.6 meters per second squared. And I don't remember what the force of gravity on Mars is, but the idea is this little g is dependent on where you are in the universe. But since we're going to spend most of our time here on Earth, that we're kind of memorizing 9.8 meters per second squared is not a bad idea. So in this case, if little g is 9.8 meters per second squared, then what's the force of gravity on this 10 kilogram object?
Well, you would multiply 10 and
9.8
Mhm.
times 10 kilograms and second squared.
Yeah, so you get kilograms meters per second squared, which is in newtons, so the force of gravity will be in newtons.
Yep.
right.
But what about the number?
98.
98 newtons.
98.
So I would have to lift it, I'd have to at least apply 98 newtons, and actually just for a brief fraction of a second, do 98.00001 to get it moving, and then once I got it moving, I could, as long as I balance the force of gravity, it will keep moving up. And then if I produce less than 98, gravity will start to pull it back down. But then I can balance it again and get it to the height that I want it to. So basically, this is essentially the force I have to apply to move it.
Got it. So to figure out the force you need to move an object, you use that equation.
Indeed.
Nice.
So this is the force of gravity.
Awesome.
Now, so that's really all there is to gravity.
Nice.
Pretty simple. I
Now,
imagine friction is a bit more complicated.
well, we had to do gravity first, because
Right.
without the force of gravity, you can't compute the force of friction.
Mm-hmm.
So gravity is a force that works downwards. But if you're trying to move an object along the floor, you notice, hey, I have to push it to get it to move, but gravity is only pushing down. So if I'm pushing sideways, nothing should be stopping me.
This should be
It should be easy. I should
easy.
have to apply almost no force. And if you're on a really slick floor, that's the truth.
Mm-hmm.
Because there's no friction.
Yeah, but with friction, it turns out the friction force is proportional to the force of gravity. Because the force of friction is equal to the force of gravity times something that they call the friction coefficient. And my memory is all of a sudden escaping me at the moment.
That's why we have books.
We write it down so we don't have to remember.
Well, it would have been helpful if I had remembered. But let's see. This won't take too long.
This is like a formal video.
Oh no, this is not a formal video. Let's see, just look it up in the index. So yeah, I just want to use the right. I want to use the. So there's variables people intentionally. G is typically used for gravity. And there's a constant or a multiplier here that people typically use to multiply the force of gravity by to get you the force of friction. So there we go. So friction. Not fusion, friction. There we go. Coefficient of 93 through 95. Where's the coefficients? It's mu, it looks like.
Mu?
Yep. It's a Greek letter. People use. Yep.
A Greek letter.
Yep.
Okay.
Mu s. This is the coefficient of static friction.
So you kind of.
And there's different kinds of friction. You notice when you go to push an object, and I'll call this friction static. Then there's F, friction. I'll call this moving is equal to F gravity. You notice if you go to push something, sometimes you can't get it to go, but if you can really push hard and get it going, it gets easy. Then it's easy to keep it moving.
Yeah.
That's the difference between the force of static friction and the force of moving friction. When you have a static friction force, it's actually it takes more force to overcome that. Then once it's sliding, then you change from then the friction force changes to the force of moving friction.
Is that okay?
Yeah, that's
Is
okay.
that
Okay, yeah.
Okay, yeah.
That's okay. I can see that's okay. Mu.
So now I can't, let's just say it's too heavy for me to pick up. So I'm like, maybe I can push it where I need it to go.
Yeah.
All right?
No,
So let's say,
gravity is only moving downwards. So this should be really easy to push if I move it this way, right?
so I'm going to set mu s equal to 0.2 and mu k equal to 0.1. All right?
Got it. Mu s equals 0.2 and
Mu k equal 0.1.
So now originally I needed to, as you remember, if I wanted to pick this object up, I found that the force of gravity was 98 newtons. And let's say I just can't do that.
Yeah.
All right? But what if I just want to slide it? So what force would I have to, if I needed 98 newtons to pick it up, which is the force of gravity, how much force do I need to get it sliding?
To get it sliding, we're working with the friction static first. So we multiply 10 by 0.2?
No.
No.
The force of gravity is not 10.
Oh, right.
What is the force of gravity?
it's
The force of gravity is 90.
98.
Right.
This is 98.
So we have to multiply 98 times
0.2.
0.2.
Which is 19.6.
19.6 newtons. That's a lot less than
Yeah,
98.
that's way less.
That's why it's easier to slide things than it is to
Yeah.
pick them up. And then I notice once I get it sliding,
It's really easy to slide.
then how much force do I need to apply to keep it
Let's
sliding?
see.
Because remember, the static friction force
98 times 0.1.
No, we multiply the static friction force by... no, okay, we multiply.
98.1. 98 times 0.1.
Otherwise.
9.8.
9.8 newtons. Yep. So remember, if I'm pushing, so now I want you guys to get the directions here figured out. If I'm pushing the block this way, the friction force is always it's like there's somebody always on the other side of the block pushing against me. All right?
Okay.
But it's always going to be a fraction of the gravitational force. It's never going to be more than the force of gravity.
That would make no sense.
Yeah, you can't have a friction force that is greater than the force of gravity itself. You could have a really crunchy surface.
Yeah, you could have like gravel.
It's really hard, where it's almost equal to 1. You know,
like
where,
sanding paper.
Where μs is close to 1, but it's never going to be greater than 1.
Or even say mud. Actually, that's not as hard as gravity would be.
It would slip.
It would just slip.
But you would slip. It'd be harder for now. There gets into how, F me, because I'm not just lifting, I'm pushing, I have to be concerned with what traction I can get.
Right, that's traction, not friction.
Well, traction is friction.
Oh.
Your ability to push on an object depends on you generating enough traction to keep you from slipping.
Ah, so traction is like a force you apply.
Yep, on the ground.
Okay.
It's like you pushing down on the ground.
But that gets more complicated. I think at this point...
Let's just focus on friction and
Well, just friction.
And gravity. Gravity.
Right.
Let's say you have no force in this.
So now we're going to look at a more interesting case. We've looked at just, gravity pushing down and we're pulling up, or friction, we're pushing and friction is pushing back.
Yeah.
So this is all x direction. The other stuff was all y direction. Now we're going to do something a little bit more interesting that ties in the stuff that you've been studying on vectors.
Okay.
We're going to look at a more interesting case, because now we're going to put everything on a ramp.
Oh, a ramp. Okay.
Alright.
So let's say there's a 90-degree angle there. This is, say, a 30-degree angle. And we're going to put our 10 kilogram mass on this ramp. And this is nice. If we want to go down, then we'll look at the case of going down the ramp first.
That's gotta be fun.
So F me is here.
Mm-hmm.
I'm going to push this thing down the ramp. Alright?
Alright.
And we're going to keep mu static equal to 0.2 and mu kinetic equal to 0.1. So we don't have to redo those calculations. But now things are on a ramp. So remember, gravity is always pushing down. So you can think of it as there is a triangle here. It's not this triangle necessarily, but it's related to this triangle.
It's that smaller triangle in there created by the creator.
So that's a 60-degree angle, and the way we would do this is there's a 90-degree angle there, right? If this is 30, this is 60, this is 90. Well, if this is 90 and this is 30, then this angle has to be 60.
Mm-hmm.
Yeah.
Because 3 angles in a triangle. Now there's another triangle here I can make with this 60-degree angle, which makes this 30. So these are actually similar triangles.
Mm-hmm.
But the reason we need this other triangle is this side of the triangle is the force of gravity.
Oh.
All right?
Okay.
So the length of this side, and we know that that's 90 newtons, right?
Right.
Yep.
So now I want to figure out the component forces, right?
Right.
To figure out static friction, I need to know what fraction of that force is pushing this way. And to figure out how well I can go down the ramp, I need to know what fraction. Remember, this is going down, but it isn't going straight into the... Right? So I need to break this up. So now this is my new coordinate system. This is x, and this is y.
Okay.
So gravity isn't just pushing down in y anymore. It's actually got an x component, right? That's why if you're on a ramp, gravity actually helps you get it down the ramp, because it has
So with the ramp, it obtains an x component as well. It's not just a y component.
Exactly. So we need to figure out what the size of these components are. Now, in this triangle here, we know the hypotenuse is 98 newtons.
Right, it's 98.
Not 90, sorry. So if we know the hypotenuse is 90, then we need to figure out what the sides of this triangle are. Because this side is the force pushing into the ramp.
Mm-hmm.
This side is the force that's helping us go down the ramp.
Right.
So which force do you want to do first?
That's force that's going down the side of the ramp.
Right. So we want to figure out essentially the x force here.
And we can figure that out by using cosine, I want to say?
Cosine of what angle?
Oh, right.
Remember, here's the hypotenuse. Well, I'm not saying cosine's wrong.
No.
You can't just say cosine.
Cosine of the 90-degree angle?
Well, no. It's never of the 90-degree angle. It's either the 60 or the 30.
Okay. 60.
Cosine of 90 is 0.
Oh, right. 60 degrees.
Remember, think about the definition of cosine. Cosine of some angle is adjacent
over
side over hypotenuse. So you got to pick an angle first to know what the adjacent side is.
The 60-degree.
Yeah, 60 degrees. This is the adjacent side. That's the side we want. So that's the force we want to calculate. The hypotenuse we know. So cosine 60 is equal to F. I'll call it me plus. It's the force that's going to help me. We call it Fx. Fx gravity. That's actually a better thing to call it. It's going to be the force of gravity in the x direction over the hypotenuse, which is 98 newtons.
And the cosine of 60 degrees is 0.5 or a half. No.
I don't believe so. Wait, no, yeah, it is.
Yeah, it is.
It is. You're right. So it's 1/2. 1/2 is equal to Fx gravity divided by 98. So how do I get Fx gravity by itself?
Multiplying both sides by 98.
Yep. Half of 98 is 49. All right. So there we go. That is the force that's helping us.
Yep.
Now there's a force that we have to calculate that isn't helping us from this. And that's the static friction force. And the way we compute that is we have to know first what force gravity is pushing this thing into the ramp. Because that's how, essentially, we know how much gravity is pressing on the ramp, and then we multiply it by the static coefficient, then we figure out what gravitational force we have to overcome, how much friction is pushing against us. So it isn't 98 times 0.2 because not all the force of gravity of this thing is pushing into the ramp. A component of it is. So how do we compute that? Well, we need trigonometry again. We need to use, we need this side over this side. And what
the sine of 60 degrees.
Sine of 60 degrees, right.
Which is
sine of 60 is going to be the opposite side from the 60, which is this side.
Sine of 60 is 0.866.
Which is going to be Fy gravity all over 98.
Okay,
and this is and sine 60 is 0.86.
Right, so once again you multiply both sides by 98.
And that times 98 is 84.87.
Yeah, if you round up, it's 84.8. So.
84.9.
9, right, round up.
Around 84.9 newtons.
Yeah.
So that's the force of gravity. Now we know how hard the object is pressing into the ramp. Now we can compute the static friction force.
Cool.
So F friction static is equal to 84.9 times mu s,
2,
which is equal to
16.97.
All right. So now we know two things here. We know Fx gravity is 49. So the gravity is providing 49 newtons of force in this direction. Friction is pushing back with 16.97. Well, if I call that a positive number, what sign should I assign to this?
Negative?
This is negative because it's pushing against.
Yeah.
If this, in fact, I'll call this Fx gravity here now.
Total force.
And the reason is because I don't have to push, right? If Fx gravity is 49 newtons,
That's really
That's
good.
enough to
And the
overcome
static-
the friction
it
stats.
will overcome the static friction force, and the ramp. This thing will go down the ramp all by
Nice.
itself.
Yep, and the total force being applied is 49
And the- yeah.
plus 6.
So F total.
9, 7, negative. It's 32.03.
It's
So
49.
we have enough gravity. We still have enough gravity that block is going to go down all by itself.
Around 32 newtons.
Mhm.
Yep, 32 newtons of force is going to.
That's a lot.
That thing won't just go down, it'll go down faster and faster and
Yeah.
faster until it gets to the bottom. So that's how you apply the force vector stuff that we learned, how to compute component forces, right?
Right.
To this problem, remember? And so it's very important to keep track of the directions of forces, right? This force here, this y gravity force, isn't stopping us from going down the ramp exactly. It's only needed to calculate the friction force, which is stopping us. So the bigger this is, the harder it is to go down the ramp.
Yeah.
But because the sliding friction coefficient is only 0.2, it's not going to be enough to stop it.
It's a nice slick surface.
It's a little rough, but it's not.
It's a tiny bit rough, but it's still.
It's not like
pretty
ice.
slick.
Ice, you wouldn't. It would.
Ice has no friction.
It's
force.
really small. It's
Yeah.
much smaller than 0.2.
Yeah.
So yeah,
Point
so
two.
that's the kind of problems we're going to work in our homework.
Yeah, the ice is like 0.0 something.